In today's video, we're going to go over 3 different methods for the hydration of alkenes and why you might choose one over the other. The first one is the acid-catalyzed hydration of an alkene. And so the first thing to note is when you're doing this, you want to make sure you're choosing a non-nucleophilic acid. So sulfuric acid, like is shown here, is a good option. Another good option would be nitric acid or HNO3. Which we have seen a couple of times before. I'm going to redraw sulfuric acid so that I have a bond here. And if I redraw that, that's no longer a 2. And just like HBr addition to an alkene, the first thing that happens is the alkene attacks the proton and gives electrons back to the bisulfate ion, and that's going to give you the more stable carbocation, so in this case the tertiary carbocation, with H adding to the carbon with the most H's. In the second step, water is going to come in and attack the carbocation, to give the hydronium intermediate, which can then be deprotonated. To give an alcohol. And I've dropped a couple of H's here. You can go back and put them in, just like that. Some important notes about the mechanism. This goes through Markovnikov addition. It has a carbocation intermediate, which means you've got to look for rearrangement. And it's the microscopic reverse of the acid-catalyzed dehydration, or the E1 elimination of an alcohol, which means that the intermediates of the E1 elimination of an alcohol are the exact same as the acid-catalyzed hydration of an alkene. The difference is that it's the exact reverse of the process. And so if we look at this reaction here, I'm going to erase my arrows. Here. One more arrow. I'm going to put my hydrogen back here. And the first thing that happens when we're going in reverse is this thing protonated to form this hydronium ion. The next thing that happens is water leaves to form this carbocation. And finally, some base, maybe water, could come in and deprotonate that position to give you this alkene. So it's the exact same process, just in the opposite direction. Let's look at another example of the acid-catalyzed hydration of an alkene. And so the first thing that's going to happen here, like before, is that this alkene is going to attack that proton, and that proton is going to give its electrons back to the bisulfate ion. This is going to form the most stable carbocation, and so in this case it's a secondary carbocation, and my H went on the primary carbon, or the carbon that had 2 H's on it already. Unlike last time, this carbocation can do rearrangement, and so I'm going to do a ring expansion here to give me a 5-member ring, and my positive charge is going to move to that secondary position. If you're having trouble seeing that, this is carbon 1, 2, 3, 4, 5, and 6. Carbon 1, 2, 3, 4, 5, and 6. This bond between carbon 3 and 6 got moved to between carbon 2 and 6, and so carbon 3 lost a bond. It now has a positive charge. the next thing that's going to happen is I'm going to sprout this hydrogen and do a little hydride shift to form the tertiary carbocation, which can then be attacked by water to give this hydronium cation intermediate, which can finally be deprotonated, likely by another water, to give you the ring expanded product of the tertiary alcohol. I think this is the major product of this reaction, but it's probably not the only product of this reaction. There are a couple other carbocations that are formed in this reaction, and so I expect that this carbocation here could have been attacked, and that would give you that product. I also expect that this carbocation could have been attacked, and so that would give you this product. Again, I think this tertiary tertiary alcohol is a major product, but these two products definitely are going to form in some capacity. The next type of reaction that we'll talk about for hydrating alkenes is oxymercuration demercuration. The first thing I want to show here is drawing out this mercury ion. This is mercury acetate. And mercury acetate is a electrophile, and so it's going to pick up some electrons. And just like the bromonium ion, mercury has some extra electrons that it can give back. And so you form our second 3-membered ring with a heteroatom with a positive charge. So 3-membered ring, mercury is a heteroatom and it's got a positive charge. And we open those by attacking the most substituted spot and kicking those electrons off. And then water can come in again and deprotonate this to give you this mercuric alcohol intermediate. In a second step, we're going to add sodium borohydride and base. And this is going to be a magic reaction. It just replaces the mercury with a hydrogen. I do not expect you to know the mechanism for how that happens. It just happens. Some important notes about the mechanism. It gives you Markovnikov addition without rearrangement. The first step is anti-addition, just like Br2 addition to an alkene, but the second step is not selective. And so the overall reaction is a non-stereo selective reaction. Let's look at another example of oxymercuration demercuration. And so the first thing I want to do is redraw this mercury acetate to show some bonds. And mercury is a Lewis acid or an electrophile. And so it's going to accept some electrons from the nucleophilic alkene which is going to kick off an acetate. But mercury also has some spare electrons that it can give back, just like the bromonium ion. And so it is going to give those back. And form this mercury ion. This is a 3-membered ring with a positive charge. Those all open the same way. This oxygen is going to attack the most substituted carbon. So that's here. You kick up electrons to mercury. To form this intermediate. Which is going to get deprotonated, likely by water. To form this intermediate. Finally, we're going to add sodium borohydride and base, and in a magic reaction, that mercury is going to be replaced by a hydrogen to give you the Markovnikov addition product with no rearrangement. The last type of hydration of an alkene I want to talk about is the hydroboration of an alkene. And just like oxymercuration, demercuration, this is going to occur in 2 steps. The first is the addition of a borohydride across the alkene. And this occurs in a syn addition. And so unlike most times we are adding an H and a water across the alkene, the H is not the first thing to add. But we're going to give some electrons from the alkene to the boron, and then the hydride, or the bond between boron and hydrogen, is going to come and go to the most substituted carbon in that alkene. And that's going to give you an intermediate where the H goes to the most substituted carbon and the boron goes to the least substituted carbon. The same reaction is going to occur 2 more times so that we get rid of all the H's on boron and form this intermediate right here. Then in the second step, we add hydrogen peroxide and NaOH, which generates a peroxide anion, or this compound here. This is going to add to that boron. Like this. And I'm going to not draw out all of those groups, but just the one. Like that. That gives boron a minus charge. And this alkyl group can do a migration and come to that oxygen, which is going to kick off this hydroxide to give you this. this intermediate. And just like before, that's going to happen 2 more times to give next. A hydroxide ion can come in and attack bromine or boron to go back to an anionic intermediate, like so. And lastly, this pair of electrons can come in and grab a water or a proton off of water to release the final product, which is the anti-Markovnikov addition of water across that double bond. So that mechanism is quite complicated, but I don't want you to know all of it. I wanted you to see it once, but the important things that I want you to know is that this first step occurs with syn addition. So the hydrogen and the boron are added to the same side of the alkene. I don't expect you to know the mechanism for how that boron gets converted to an alcohol, but I do want you to know that that occurs with retention of configuration, and so the net addition is syn for this reaction. To reiterate some important notes about the mechanism of the hydroboration of an alkene, it's always going to give you the anti-Markovnikov product. The first step is going to be syn addition of the hydrogen and the boron. The second step occurs with retention of configuration, where the boron is replaced by oxygen in the same spot, which means that the overall reaction is the syn addition of a hydrogen and an alcohol across a alkene. Let's take a look at one more example. And so here's an alkene and BH3. And we're going to do syn addition across that carbon-carbon double bond to give this. And that's really the only part of this mechanism I want you to know. The next step is just magic. And it's going to give you the anti-Markovnikov addition of water across that alkene.